So good morning. Thank you very much for the very kind introduction. And in particular, also thank you very much for the opportunity to be here this morning. Yeah. What I will do in the next 15 minutes also is give you a very brief overview of one of the technology that we hope will help us address some of the computational and simulational challenges that we face. Yeah. So I will make a very few introductory remarks, put it in a kind of a historical context, and then describe some opportunities and challenges around quantum computing. Yeah. Just to tell you that that quantum computing is something that you should be aware of. It's now the topic also of thrillers. Yeah. And if you read this thriller, you know, they even reference papers directly. Yeah, so that's something that I'm very proud of. You know, it doesn't happen very often. Yeah? Anyway, you know, every time you open the newspaper, if you still read newspapers on paper or watch the news or listen to the radio, you probably can't hear anymore the stories of the Fourth Industrial Revolution. Yeah. But next to the Fourth Industrial Revolution and the development from the steam engine to where we are today, there's also been two other revolutions, yeah, in the quantum domain. Yeah, one around 100 years ago when people like Einstein, Heisenberg, and Schrödinger developed what we call these days quantum mechanics. Yeah? And that is a very successful theory that gave us the transistor, the laser, and diodes and things that were fundamental for the third industrial revolution already. Yeah? But since around 30, 40 years, we are in the midst of a so-called second quantum revolution, yeah, that uses as a resources all the crazy properties, if I may say so, of quantum mechanics, yeah, like entanglement and similar things. Yeah? And these spooky properties of quantum mechanics are now really used as tools. Yeah? So essentially what we have been experiencing over the last 30 years is that two of the most prominent scientific disciplines of the last century started merging together. Yeah, quantum mechanics and information science are now one new discipline that some people like to call quantum information science. And this quantum information science has three main pillars. Yeah? The computing part, the communication part, and the sensing metrology part. Yeah? And these three pillars are the foundations of the vision of a next generation quantum-based internet, yeah, that many people worldwide are working toward its realization. Yeah? I will only speak about the quantum computing part now, yeah, but maybe on another occasion we can touch on the other topics. Yeah? So why is there this big fuss about this second quantum revolution? Mainly because quantum metrology promised to give us, and already gives us, the most precise measurements that we've ever made. Yeah, so this is really something new. Yeah, quantum communication gives us the opportunity to transport data securely based on physical principles, not on mathematical complexity. Yeah, you know, all our encryption schemes are based on the fact that they're not impossible but difficult to crack. Yeah. Whereas quantum cryptography offers ways to share secret keys with a security that is based on physical. So you need to break the laws of physics to break that level of security. Yeah? And last but not least, quantum computing promises to give us algorithms that will beat classical algorithms once we have the appropriate hardware. Yeah. The story of quantum computing started also 40 years ago, yeah, with Richard Feynman, a famous Caltech professor, Nobel Prize winner, who had the intuition that to say that to realize that you know, nature at a fundamental level is quantum. Yeah, we're all made of atoms and molecules. Yeah, so those are obviously quantum. Yeah. So that probably the best way to simulate the quantum world is to have a machine that operates according to quantum principles. Yeah? So this was maybe the birth of quantum computing, at least as an idea. Yeah. Before I tell you the rest of the story, let me give you a brief statement on the worst case scenario. Yeah, because there's lots of hype about quantum computing, and companies that produce them or try to build them promise lots of things. Yeah, that might happen or might not happen. Yeah, but there is already a worst case scenario that we can state securely. Yeah. And that is, in the arsenal of gadgets, for instance, for computing. Yeah, we have CPUs, GPUs, FPGAs, ASICs, and so on and so forth. Yeah, and we know already that quantum devices are good at solving some aspects of calculations, for instance, for machine learning, yeah, and beat classical devices. And so the worst case scenario is that we won't have a universal quantum computer. We will have just a kind of a quantum card to put in a computer that will solve a certain specific task in a very efficient way. So that's the worst case scenario, which is already implemented. Yeah. Of course, the final aim is to have a universal quantum processing unit, and many people are working towards that goal, and I will say something about it just now. So let's move to opportunities of quantum computing. I haven't told you anything about quantum computing and quantum computers in detail yet. And I will show you only one slide because we have 15 minutes, so we will keep it very, very high level. Yeah. Traditional computing is based about the manipulation of bits. Yeah? And bits, 0, 1 are essentially, there is a current, there is no current, the switch is on, the switch is off. Yeah? But of course, at a very small scale, so that you can have many, many of those and manipulate them very fast. Yeah? Quantum computing is based about the quantum version of the bit, yeah, that people familiarly call now the qubit. Yeah? And the qubit is a completely different object, yeah, because it lives in the quantum world. Yeah? Technically, it's called the Hilbert space. Yeah? And you can geometrically visualize a quantum bit as a vector, yeah, that goes from the center of a sphere to the surface of the sphere. Yeah? And in quantum mechanics, because of the rules of quantum mechanics, every point on the surface of the sphere turns out to be a legal qubit state. Yeah? So you already see by this visual contraposition that there's much more going on in quantum mechanics than in classical computing. Yeah? And on this so-called blosphere, we identify the 0 qubit between these funny angular brackets as the north pole and the 1 qubit as the south pole. Yeah? And one of the strange things of quantum mechanics is that when you measure this qubit, you will measure either 0 or 1. Yeah, but in between, the qubit can be a little bit everywhere. Yeah, and these degrees of freedom opens up opportunity to do algorithms that are completely different from the classical ones that we are accustomed to. Yeah. So since the 80s, yeah, since this vision of building quantum computers, many people tried very hard to come up with quantum algorithms. Yeah? And for instance, in the early 90s, people like David Deutsch and Richard Yost that came out with the first kind of model algorithm that showed that in principle, a quantum machine could solve certain classes of artificial problems in a way that scales better with complexity than classical algorithms. And it kickstarted a whole search for quantum algorithms. Yeah? But the first really big breakthrough, and you see the algorithm in red at the bottom, yeah, was achieved by Peter Shor, yeah, in 1994. Yeah? And he showed that a quantum machine can factorize large integers much more efficiently than classical machines. Yeah? This is on paper, yeah. This is very important and shook a little bit the community because, as you know, all our encryptions, most of our encryption schemes, like the one that you use traditionally on when you buy something on the internet, yeah, are based on this fact. So it means that once we have a big quantum computer, today's encryption methods will be threatened. Yeah? So that we need to start thinking about alternatives. Yeah? And since then, many other algorithms have been developed. We know that the quantum computer can search stuff faster. We can do linear algebra much better on a quantum computer. We can do optimization and so on and so forth. Yeah, and there's lots of interest in application these days on machine learning. Yeah. The reason is explained on this side, where you see, I won't go into details, but what is already evident just by looking, is that the classical the quantum version of the algorithms has lots of square roots and logs, and that means really, in the case of log, exponential speed up in computing time versus complexity, and even for machine learning algorithm, you can observe the same kind of scaling behaviors. There are, of course, and sorry, I quickly finish the opportunities and then move on to the challenges, because I see we have just 5 more minutes. There are interesting use cases, where people really hope that quantum computing will make a difference. And it's, for instance, development of new materials, for instance, for carbon capture, or tackling the spreading of antibiotics in wastewater, or eco-friendly fertilizer production. This is just producing fertilizers is a very expensive business, but bacteria do it for free, and we don't know how. So these are really challenging simulation tasks. Also, in view of climate change, how we will make sure that we keep feeding the 8 billion people that live on this planet. So these are really complex problems with many variables that require that we pull all triggers to solve them. Or in in the pharmaceutical context, how we can optimize vaccine distribution. These are all big tasks where we are hopeful that quantum computer will help us. What are the challenges? The challenges is that we don't have a computer. At the moment, what we have are so-called noisy intermediate scales quantum computers. They are quantum computers that, in principle, don't have error correction, because we don't know yet how to scale the number of qubits to sufficient number. This is a term that was coined 4 or 5 years ago by John Preskill. The best that we have today in this class of noisy intermediate state quantum computer are 1,000 qubits. And these were announced just a few days ago by IBM. So from a technological point of view, there's still lots to be done. Also, a few days ago, another team announced that they are now able to produce a quantum computer that has around 50 logical qubits. And these are error-corrected qubits. This is a really huge step. That will probably boost the search for universal quantum computers no end. Because this is a step that we've all been waiting for a long time. So things are moving now apparently quite quickly. So when can we expect this quantum supremacy advantage or practicality? Let me skip this quickly. You can do a very simple comparison, and it was done by Matthias Troyer and his co-worker just also a year ago or so, where you compare what you can do these days on a standard NVIDIA GPU compared to a 10,000 logical qubit machine. Today we have only 48. So it's a long way to go. So and you realize very quickly that there are some bottlenecks that where we really need to do things better. And one is how we input classical data in a quantum computer. If you want to speed up ChatGPT, the challenge on a quantum computer is the input of data. And you see that on a classical GPU, it's a factor 10,000 faster today. So there is long to be done. So that the outlook at the moment, but things are in flow and might change very quickly, is that quantum computers will be practical in the short term, and maybe short term means a PhD time scale, 3-4 years. For big compute problems. There are problems where we have small data but large computational need, but not for big data problems. That will take probably a little bit longer. And since I'm running out of time, maybe I skip these more technical things and come to slowly to an end, so that very practical, the simulation of quantum systems. So the original idea of Richard Feynman, we build quantum machine to simulate quantum system, is what quantum computers will be good now, in the short term. That means quantum chemistry, material sciences, quantum physics, and things like that. For things like machine learning or searching or Monte Carlo simulation, they're still quite unpractical, because most speedups are polynomial, are quadratic quartic or something like that at best, yeah. And we expect, and we need really exponential speed ups to make a big difference, yeah. So I think I have 15 more seconds. So I think I managed to come to an end on time. So thank you very much for inviting me. And of course, I'm happy to answer questions now or later during the discussion round. Thank you very much.